In this problem, we were asked to factor the polynomial over the real numbers. Now, I'm going to take this problem a little bit further than that and even sketch a graph of it towards the end of the problem. So I'll make a note when we reach the end of where the instructions actually told us to go. So we have this fourth degree polynomial, and we want to factor it completely. Well, factor it over the real numbers. In this particular problem, we can't factor it completely if it's over the real numbers. So let's get started. The first thing that I want to do is consider Descartes' Rule of Signs. If we want to look for the positive real zeros, we look at the sign changes. That's positive, 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 and then it changes one time to negative, right? So there's only one positive real zero in this polynomial. The negative real zeros, we need to substitute in a negative x. If you substitute in a negative x here, you're going to get a positive 2x to the fourth. A negative to a third power is going to be a negative. A negative squared, that's still going to be a positive. This negative times this positive would end up being a negative. And the 63 doesn't change. So from here you can see the sign changes positive to negative. That's one time. That's two times. That's three times. And then it doesn't change again. So the negative real zeros, there will be either three of them or one of them. So now we can start working with our P's and Q's. So P is going to be negative 63. Q is going to be a positive 2. Now we need factors of both of these. So for our negative 63, we have positive and negative 1, 3, 7, 9, 21, and 63. I think those are all the factors of 63. And for 2, we just have positive or negative 1 and 2. Now we list all of our P's over Q's. Sorry, my dog's barking. So we have plus or minus. I'm going to have a big list here. So put 1 over 1, 3 over 1, 7 over 1. So put all of them over 1. And then put all of them over 2. So 1 half, 3 halves, 7 halves, 9 halves, 21 halves, and 63 halves. So these are all the possible rational zeros of this polynomial. Now remember, there's only going to be one positive one, and there's either going to be 3 or 1 negative ones. So in this list, we can either work with negative ones, so like try negative 1, see if it works. We could try positive ones. I actually want to show you something whenever we try some of the positive ones. So let's try the first one in the list, which is a positive 1. So I'm going to do 1 stow x enter. So I'm trying this 1 right here. I'm going to plug it into the polynomial. So we have 2x to the fourth plus 13x cubed. It's hard to see my screen, sorry. Plus 11x squared plus 117x minus 63. Let me make sure I got that typed correctly. And it looks like we need to focus a little bit. There we go. 2x to the fourth, 13x cubed, 11x squared, plus 117. I think it's right. So if we try 1, we get 80. Remember, we're looking for 0, and that doesn't work. So let's go to the next one in our list, which is a positive 3. We get 900. So it seems like if we keep going down this list up to the 63 and we try these values, then the result is just going to keep getting larger. So let's stop that path. maybe we should try the negative one, or maybe we should try one of these fractions. Either way is totally fine. I think what I want to do is try the 1/2. So 1/2 stow x, enter. And then we test, oh, we get 0. So this is a good thing. We stop, we try the 1/2 in our synthetic division. So we have 2, 13, 11, 117, and negative 63. Remember, you bring down the 2 and multiply. Half of 2 is 1. Then you add 13 plus 1 is 14. Multiply. Half of 14 is 7. 11 plus 7 is 18. Half of 18 is 9. 117 plus 9 is 126. Half of 126 is 63. And when you add those, you do get 0. Now remember, if you don't get 0 there, then something's wrong, because we did it on the calculator and we know it's supposed to be 0. So now this becomes 2x. Remember, the original was the 4th power, right? So this one becomes 2x cubed plus 14x squared plus 18x plus 126. So now we have a new polynomial that we need to factor. Just don't forget about this guy, because that's one of our zeros. Okay, it's going to create one of our factors. If you notice, we have a 2 in common with all of these. So let's go ahead and factor out that 2. What is that? 63. All right. Now this is going to be, we could use factor by grouping on this. If we could not factor by grouping on this part, then what we would have to do is start over with p's and q's and use these values instead of the original ones. All right. So let's factor by grouping. Don't forget about that little 2 stuck out front. So we can factor an x squared out of the first 2. We'll be left with an x plus 7. We can factor a 9 out of the second 2, and we'll be left with an x plus 7. Now we can keep that 2, factor out the x plus 7. If you take that out, you're left with x squared plus 9, right? So we have x squared plus 9. So it looks like we're almost finished with our factoring. We bring this one down. So we're going to have, I'm going to put the 2 out front. Then we're going to have x minus that number, and then these 2. Now whenever you have a fraction involved, usually if you multiply that constant that's out front, if you multiply it by that particular factor, it'll make the fraction go away. Doesn't always work that way, but usually it does. So let's distribute the 2. We're going to have p of x is equal to 2x minus 1, that's distributing the 2, x plus 7, and x squared plus 9. Now this is factored over the real numbers. This is the one that they asked us to do in the problem. Now what if they asked us to completely factor it? If they asked you to completely factor it, all of your x's have to have an exponent of 1, and this one does not. So if you do x squared plus 9 equals 0, subtract 9, take the square root of both sides, and don't forget plus or minus, you get x is equal to plus or minus 3i, right? Well, in that case, you would need to do x minus 3i and x minus a negative 3i. So if you were asked to completely factor, it would look like this. This would be completely factored. Now, keep in mind this problem didn't ask us to do that, but that's what it would be if they did ask us to do that. Now, we have it completely factored. We also know what the zeros are. We have real zeros here and imaginary zeros here, which means they're not really zeros, right? Because zeros, you have to be able to graph them. So, let's bring this over to the next page. To copy it down. So p of x is equal to 2x minus 1 x plus 7. I'm going to go ahead and use the completely factored form. So x plus 3i and x minus 3i. So if we're asked to find the zeros, you would have 1/2. We already found that one on the previous page. If you set this one equal to 0, x is equal to -7, and if you set both of those equal to 0, you would have a positive 3i and a negative 3i. So those are the real and imaginary zeros of this polynomial. If you are asked to find the x-intercepts, those only happen at the real zeros, right? So you would have an x-intercept at 1/2 0 and at -7. Oops, that's supposed to be a 7 right there. -7 0. Sorry about that. If you are asked to find your y-intercept, it's probably easier to go back to, whoops, I went too far. Probably easier to go back to the original function. If you plug 0 in for x, all those go to 0 and you're just left with the -63, right? So your y-intercept is the point 0, -63. Now, this original function is a 4th degree polynomial, which means it has a general shape like a parabola, but it could do crazy stuff in the middle. Okay? So that means that it goes up on the left and up on the right. So if you're asked for the end behavior, you can say up on the left, up on the right. Now, that's not the technical way to say this, so I'm going to write the technical way. As x approaches -infinity, that's this way. As x goes to -infinity, y goes to infinity. It goes up. As x goes to +infinity, that's this way, y also goes up. So y goes to infinity. So if you're asked to be technical about it, it would look like this. And that is a negative right there. Alright, so then we need to know about some multiplicities. Multiplicity means how many times each of the zeros occurs. Well, this one and this one only occur once, right? These two only occur one time. So all have multiplicity 1. That means that they are all cross points. Okay? If any of these has an even multiplicity, so if this had a little 2 right there for squared or fourth, something like that, then it would become a touch point. So let's see how this works on a graph. Now with a y-intercept of -63, I'm not quite sure I can get it all on there, but let's see how it goes. Okay, so we have an x-intercept of 1/2 0. Another x-intercept at -7 0. I'm just going to randomly say that -63 is right there. So we'll call this 0, -63. Okay, this is all we have right now. But we do know that it goes up on the left and up on the right, correct? We also know that each of these represents a cross point. Now whenever you have imaginary zeros, that means that it's going to either come up and get close and go back down, or it's going to come down, get close, and go back up. When I say get close, I don't mean it's actually going to get close to the axis. I just mean it heads like it's going towards it. It's kind of like saying, haha, I'm not really going to make it. Like that, when you have an imaginary zero. Alright, so we know it's going to go up on the left and up on the right. We know that automatically. We know that it's crossing through this point. So how do we handle the rest of this graph then? Well, let's see. We know we have to come down and at least go through that way, but we also have imaginary zeros, right? Just so we can get an idea of the graph, my window is not going to be quite right for this one, but I'm going to show it to you anyway. So it looks like we have a little squiggle going on right there. I don't know if you can see that on my graph. Let's go out a little bit. I need to see more in the negative direction here. Let's go down to -70. See what that does. That's still not enough. So change my window again. Let's go to -200. Yeah, we're still not getting there, right? So let's change the window again. Oops, don't clear that. Let's go to -500. Wow, we still need some more, but it looks like we're getting a little bit closer to the point in our graph at the bottom. So change the window. I'm going to go crazy and put -1000. And now we can see it. Do you see how it does that little squiggle right there? So it's going to come down, go back up. It's going through that -63 and it's coming back up. So this particular graph goes way down there somewhere. Comes back up, does a little squiggle, and pretend like that goes through the 1/2 right there. That is what this particular graph looks like.